Hi, I want to look at another example of a connected object problem. Only instead of having the objects connected in what's obviously a straight line, objects are connected making use of a pulley. Now, anytime we have an ideal pulley in physics, it's not contributing anything to our system except taking the tension in whatever cord is running along that pulley and redirecting that tension undiminished to the other object on the other end of that cord. So here I have a 422 Newton weight box sitting on a flat, smooth table, and it's connected to a rope over a pulley to a 185 Newton box that's suspended in the air. Now, if we want to figure out what happens, there are always two ways we can think about connected objects. We could draw a box around our entire system and look at just the forces that are acting outside our system. So if we were to do that, well, gravity is always acting outside, so we'd have the weight of box 1 and the weight of box 2 both pulling down. There's nothing externally touching box 2. But externally, box 1 is being touched by the table, so there would be a normal force acting on box 1, which we could probably reason would be about the same size as the weight of box 1, especially as long as this cable is pulling parallel to the table. So that means our total outside force is going to be the weight of box 2, 185 newtons. And if we wanted to find our acceleration, we could take our total outside force, divide by the mass of object 1 plus the mass of object 2, and that would give us our acceleration. Well, a lot of people think physicists like to do math. We do like working with equations, but we like doing math to make our lives easier. We don't like doing arithmetic. So sometimes there are a lot of tricks that you can do to avoid having to calculate more things. So we were given the weights. If we want to find the mass, we'd have to take each weight, divide by the strength of gravity, and that would give us our mass. Well, the clever but lazy thing to do is let's multiply both sides of this by the strength of gravity. Well, here I'd just be taking 185 newtons times 9.8 meters per second squared. Here, m1g plus m2g, that's just 185 newtons plus 422 newtons. That's just going to give me 607 newtons. Adding's a lot easier than dividing twice and adding more complicated numbers. So from this connected system, I should have 185 newtons divided by 607 newtons times 9.8 meters per second squared, which is right around 3 meters per second squared. Well, let's check that by looking at the force of tension, calculating that force of tension, and then we'll double check our work by calculating acceleration. So if we need to figure out the size of an internal force, we have to treat each object that's connected individually. So for drawing an isolated box just around object 1, we'd still have the weight of object 1 and the normal force from the table canceling each other out, and then we would have our force of tension pulling exactly along the x direction. Our pulley redirects that tension and we get to box 2. So box 2 has the weight of box 2 pulling it down and the force of tension pulling it up. Now if I look at box 1, there's an uncanceled force in the x direction. So I know there absolutely, positively is going to be an acceleration forward, because there's nothing holding back that force of tension. We said we had no friction. So if 1 accelerates forward, 2 has to accelerate down. So that means my tension has to be smaller than the weight of 2. So now we can apply Newton's second law. So for the first object, the acceleration is going to be that force of tension divided by the mass of object 1. For the second object, my net force, I have the weight in the direction of my acceleration minus the tension opposite the direction of my acceleration divided by the mass of object 2, and those two accelerations have to be equal to each other. So I'm not a big fan of working with fractions if I can avoid it, so I'm going to get rid of my denominators by multiplying both sides by m1 and m2. So on the left-hand side, I'd get m2 times my tension, and on the right-hand side, I'd get m1 times the force of gravity of object 2, the weight of object 2, minus m1 times my force of tension. So now, to solve for the force of tension, I can take that tension term on the right, add the mass of 1 times the force of tension to both sides, and distribute out that tension to say the mass of 1 plus the mass of 2 times my force of tension is going to equal the mass of 1 times the weight of object 2. And then, to solve for my tension, I just have to divide by these masses. Or, I could do that exact same trick that I talked about. I could do it a little bit differently. I could multiply both sides by g here, and then that would be the weight of 1 plus the weight of 2, which I said over here was 607 newtons, times the weight of 1. So what that gives me then is a way to calculate tension by saying the tension is going to be the weight of 1 times the weight of 2 divided by the weight of 1 plus the weight of 2. So I'd have 422 newtons times 185 newtons divided by 607 newtons, which is 128.6 newtons, or about 129 newtons. Now, last steps, calculating that acceleration. So my tension, I said, is 129 newtons, and again, we don't want to calculate mass, multiply and divide by g, so I'd have tension divided by the weight of object 1 times gravity is my acceleration. 129 newtons divided by 422 newtons times 9.8 meters per second squared gives me 3 meters per second squared, which is just what we calculated this way. Thanks for watching.